Right now, as you rest here, waves are moving through your body. Your heartbeat sends them through your blood. Your breath creates them in your lungs. Even your thoughts travel as tiny waves between brain cells. Waves are everywhere. The light touching your eyes right now is a wave. The sound of these words is a wave moving through air. The warmth you feel from your blanket traveled to you as waves. The earth beneath you rings like a bell with waves so slow they take 20 minutes to complete one cycle. Tonight, we're exploring these gentle rhythms that shape our world. If you enjoy these quiet journeys into science, take a moment to like this video and subscribe to Simple Science for Sleep. We explore wonder every night, and there's a whole community of people just like you who find peace in understanding how the world works. Leave a comment telling me where you're listening from and what time it is there. I love knowing we're all sharing this moment together, scattered across the world, but connected by curiosity. This is your space to discover why waves are nature's most peaceful force, a place where science becomes a lullaby. So settle in, get comfortable. Let your body sink into whatever supports you right now. Waves don't push. That's the first thing to understand. When you watch an ocean wave roll toward shore, it looks like the water is traveling forward, but it's not. The water mostly stays in place, moving in small circles. What travels is energy, passed from one water molecule to the next, like people in a stadium doing the wave without leaving their seats. Picture a single drop of water floating on the ocean surface. As a wave approaches, that drop doesn't surf toward the beach. It rises up, moves forward slightly at the crest, drops down, moves back slightly in the trough, and ends up almost exactly where it started. It draws a small circle in the water. The wave passes through. The water remains. This same principle powers every wave in existence. Sound waves move through air, but the air molecules themselves just vibrate back and forth. They don't travel with the sound. Light waves carry energy across space without moving any physical material at all. Earthquake waves shake the ground, but the earth itself doesn't flow away. It trembles in place while the energy races past. The ocean holds many kinds of waves at once. The small ripples you see dancing on the surface come from wind. The bigger swells that surfers love are born from storms thousands of miles away. Tides are waves so large their wavelength wraps halfway around the planet. All of them coexist, overlapping, interfering, combining. When two wave crests meet, they add together and create a taller wave for a moment. When a crest meets a trough, they cancel out and the surface flattens. This is happening constantly across every body of water on Earth. Waves from different storms, different winds, different sources, all passing through each other like ghosts. Stand at the edge of the ocean and you're watching the result of 1,000,000 calculations. Every wave you see is the sum of countless smaller waves, added and subtracted in real time by the water itself. The ocean is always computing, always solving the equation of how energy moves through it. It does this without thinking, without trying. It simply follows the rules written into the nature of waves. Even the rhythm of waves hitting shore follows patterns. Watch the ocean for a few minutes, and you'll notice some waves are bigger than others. They come in sets. Surfers know this. They wait for the sets, watching the horizon. The pattern exists because waves travel at different speeds depending on their wavelength. Longer waves move faster, so they overtake the shorter waves and for a few moments they align. Their crests coincide. The waves add together and create that larger set before separating again. The ocean never stops calculating these combinations. Right now, in the middle of the Pacific, in the depths of the Atlantic, in every sea and lake and puddle, waves are passing through each other, adding and subtracting, creating patterns that last for seconds before dissolving into new patterns. It's been happening for billions of years. It will continue long after we're gone. The mathematics of waves is eternal, playing out on every water surface simultaneously. Your body knows about waves too. You were rocked by them before you were born, floating in fluid, feeling the rhythm of your mother's breathing, the pulse of her heartbeat. Those were your first waves, your first rhythm. Maybe that's why the sound of ocean waves feels so deeply calming. It echoes something ancient in us, something that remembers floating in darkness, safe and warm, moved gently by forces we didn't need to understand. Sound is a wave that needs something to travel through. It can't cross empty space. In the vacuum between stars, there is perfect silence. No matter how loud an explosion, no matter how powerful a star, the sound goes nowhere. It needs matter. It needs molecules to push. On Earth, sound moves through air by bumping molecules together. When you speak, your vocal cords vibrate. They push air molecules. Those molecules push the ones next to them. The push travels outward in all directions at about 767 miles per hour. That's the speed of sound at sea level. Higher up, where the air is thinner and colder, sound moves slower. In the dense warmth of the ocean, it moves faster. The speed changes, but the principle stays the same. Sound is a pressure wave, a moving zone of compressed air followed by a zone of stretched air. Compression and rarefaction traveling together. Your eardrum feels these pressure changes, and your brain translates them into sound. Every sound you've ever heard was molecules pushing molecules. The music you love is air being squeezed and released in patterns. A whisper is a gentle wave. A shout is a stronger one. The same mechanism, different intensities. Whales understand this better than most creatures. They sing to each other across hundreds of miles of ocean. Their songs are waves traveling through water, which carries sound much better than air. A whale's call can circle entire ocean basins, bouncing off underwater mountains, refracting through layers of different temperature, reaching other whales on the far side of the world. The songs are complex. They have structure, rhythm, phrases that repeat and evolve. Male humpback whales sing during breeding season, and all the males in one region sing the same song. But the song changes slowly over time. New phrases appear, old ones fade. By the next breeding season, the song has transformed. All the males learn the new version. How they coordinate this across such vast distances, we still don't fully understand. Some whale songs contain frequencies so low that humans can't hear them. They travel as infrasound, felt more than heard. These deep notes can travel the farthest, thousands of miles without fading much. The whales use them to communicate across entire oceans. Before ships filled the seas with engine noise, the oceans were clearer. Whales could hear each other from even greater distances. Now their songs must compete with propellers and sonar, and their communication range has shrunk. But the songs continue. Waves of compressed water carrying meaning across the deep. Each whale adds its voice to the chorus, and the ocean carries every note. The water remembers nothing, but it delivers everything. It's a perfect messenger, asking nothing, taking no sides, simply moving energy from one place to another. Sound waves in air eventually fade. They spread out, lose energy to friction, warm the air just slightly, and disappear. In space, they never begin. In water, they can travel farther than you'd think possible. The ocean is full of sounds we never hear. Shrimp snapping their claws create tiny shockwaves that, together, create a background crackling across entire reefs. Fish grunt and croak. Ice cracking in polar regions groans and booms. Underwater volcanoes rumble. Earthquakes send pressure waves racing through the deep. All of it is waves. All of it is energy moving through matter, following rules that have existed since the universe began. The ocean doesn't choose what sounds to carry. It carries them all equally, without judgment, without effort. The mathematics is the same whether the wave comes from a whale song or a ship's propeller. The water simply does what water does. It vibrates, it transmits, it allows the wave to pass through. Every wave has three basic properties. Wavelength is the distance from one crest to the next. Frequency is how many crests pass a point in 1 second. Amplitude is the height of the wave, the distance from the middle to the crest. These three properties determine everything about a wave. Change one, and you change what the wave does, how it behaves, what it carries. Take sound. A high-pitched note has a short wavelength and high frequency. Many crests pass your ear each second. A low note has a long wavelength and low frequency. Fewer crests pass. The frequency is what your brain hears as pitch. Middle C on a piano vibrates 261 times per second. The A above it vibrates 440 times per second. Your ear detects these different frequencies, and you hear different notes. Amplitude determines volume. A whisper and a shout can have the same frequency, the same pitch, but different amplitudes. The shout pushes air molecules harder. The wave carries more energy. Your eardrum moves more. You hear it as louder. Light works the same way, though light is different from sound in fundamental ways. Light doesn't need matter to travel through. It moves through empty space just fine. In fact, it moves through empty space better than through anything else. Put matter in light's path, and the light slows down. The frequency of light determines its color. Red light has a lower frequency than blue light. Red waves are longer. Blue waves are shorter. Between them lie all the colors you can see: orange, yellow, green. Each color is just light, vibrating at a different rate. Your eye contains cells that respond to different frequencies. Some cells fire when red light hits them. Some respond to green, some to blue. Your brain combines these signals, and you see the full spectrum of color. But the colors aren't really in the light. Color is something your brain creates from frequency information. The light itself is just electromagnetic waves of different lengths. Beyond red is infrared. The waves are too long for your eyes to detect, but you feel them as heat. The warmth from a fire is infrared light, carrying energy to your skin. Beyond blue is ultraviolet. These waves are too short for your eyes, but they carry enough energy to damage skin cells. That's what causes sunburn. The wave frequency is high enough that each individual wave carries a punch. Waves of different frequencies do different things. Very long radio waves can travel around the Earth, bouncing off the ionosphere. Very short gamma rays can pass through your body. The frequency determines how the wave interacts with matter. Low frequency waves slide past most obstacles. high-frequency waves get absorbed or scattered. This is why you can hear someone talking in the next room, even when you can't see them. Sound waves, with their relatively long wavelengths, bend around the doorway. They spread out after passing through the opening. Light waves, with much shorter wavelengths, travel in straighter lines. They don't bend around corners as easily, so sound reaches you, but light doesn't. The ocean shows you all of this in slow motion. The long swells have low frequency. One crest might pass every 10 seconds. The small ripples have high frequency. 10 crests might pass in 1 second. Both are waves, following the same mathematics, but behaving differently because of their wavelength and frequency. Stand in the surf and you feel amplitude directly. A small wave barely moves you. A large wave, same frequency, but greater amplitude, carries enough energy to knock you over. The amplitude determines how much energy the wave transports from one place to another. Light is strange. For centuries, people argued about what it really was. Some said light was made of particles, tiny bullets flying through space. Others said it was a wave, ripples in some invisible medium. Experiments supported both views. Light seemed to be both things at once, or neither. The truth turned out to be weirder than anyone expected. Light is a wave, but it's not a wave of anything physical. It's a wave of electric and magnetic fields, tangled together, creating each other as they move through space. Here's how it works. An electric field creates a magnetic field. That magnetic field creates an electric field. The two fields leapfrog through space, each one generating the next. They don't need water or air or any substance. They are the substance. They move themselves forward at 186,282 miles per second. Nothing in the universe goes faster. This speed is constant. It doesn't matter if you're standing still or moving. Light always passes you at the same speed. This fact, this strange constancy, is what led Einstein to develop relativity. The universe has to bend itself into strange shapes to make sure light always moves at the same speed for every observer. Time slows down, space contracts, reality gets flexible, all because light refuses to speed up or slow down. Every light source is creating these electromagnetic waves. The sun does it by fusing atoms in its core. The heat from that fusion shakes electrons in the sun's outer layers. Shaking electrons create electromagnetic waves. Those waves travel across 93 million miles of empty space and arrive at Earth 8 minutes later, carrying energy from the sun to your skin. A light bulb does something similar. Electricity heats a thin wire until the atoms vibrate so much they shake their electrons. Those shaking electrons emit electromagnetic waves. Some of those waves hit your eyes and you see light. Your eyes are electromagnetic wave detectors. The retina at the back of your eye contains molecules that change shape when hit by light waves of certain frequencies. That shape change triggers a signal to your brain. Your brain interprets the pattern of signals as an image of the world. But really, you're seeing electromagnetic fields oscillating at different frequencies. Your brain translates that into the experience of vision. Most electromagnetic waves are invisible to you. Radio waves pass through you constantly. Right now, radio signals from hundreds of stations are moving through your body. They carry music, voices, data. Your body is transparent to them. They pass through without interaction. You need an antenna and a receiver to detect them, to turn those electromagnetic oscillations back into sound or information. Microwaves also pass through you, though some get absorbed by water molecules in your body. That's how a microwave oven works. It produces electromagnetic waves at a frequency that makes water molecules spin. The spinning creates friction. Friction creates heat. Your food warms up because its water molecules are dancing to the rhythm of electromagnetic waves. X-rays pass through your soft tissue but get absorbed by bones and teeth. The calcium in bone interacts more strongly with high-frequency electromagnetic waves. Hold your hand in front of an X-ray source, and your bones cast shadows on the detector. The X-rays are just light waves of very high frequency, invisible to your eyes, but visible to the right equipment. All of it is the same phenomenon. Electromagnetic waves of different frequencies, all moving at the speed of light, all following the same rules. The radio waves carrying a song and the gamma rays from a distant supernova are cousins. Same family, different frequencies, all traveling through the universe, carrying energy and information from one place to another. The sun pours electromagnetic waves across the entire spectrum. Radio waves, infrared, visible light, ultraviolet, X-rays. All of it streaming outward from the fusion at its core. Most of it flies into empty space. A tiny fraction hits Earth. That tiny fraction powers almost everything you see. Plants catch visible light and turn it into sugar. Animals eat the plants. The energy flows through the food chain. All of it originally captured from electromagnetic waves that started as fusion reactions in the sun's core. The electromagnetic spectrum is vast. The visible light you see occupies only a tiny slice of it. If you laid out all possible electromagnetic frequencies on a line, visible light would be a thin stripe in the middle. On one side, stretching to infinity, are the longer waves. On the other side, stretching equally far, are the shorter waves. Radio waves have the longest wavelengths. Some radio waves are longer than buildings. They're used for communication because they travel far and bend around obstacles. AM radio uses longer waves than FM radio. That's why AM signals can reach farther, especially at night when they bounce off the ionosphere and travel hundreds of miles. After radio comes microwave. These waves are shorter, measured in centimeters. They're used for radar, satellite communication, and cooking food. The atmosphere is relatively transparent to them, which makes them good for transmitting signals through air. Then comes infrared. Every warm object emits infrared light. Your body is glowing right now with infrared radiation, invisible to your eyes, but detectable with the right camera. This is how thermal imaging works. It sees the infrared light your body produces just from being warm. Next is the narrow band of visible light. Red on one end, violet on the other, with all the rainbow colors between. This is what your eyes evolved to see, probably because the sun produces most of its light in this range. Evolution shaped your vision to match the light available on Earth's surface. Beyond violet is ultraviolet. The sun produces a lot of UV light, but Earth's ozone layer absorbs most of it. What gets through can damage DNA, causing sunburn and skin cancer. But UV light also triggers vitamin D production in your skin. The same waves that can harm you also help you, depending on the dose. After ultraviolet comes X-rays. These have enough energy to knock electrons off atoms. That's what makes them dangerous in high doses, but useful for medical imaging in low doses. Your bones absorb X-rays more than your soft tissue, creating those familiar skeletal images. Finally, at the shortest wavelengths and highest frequencies are gamma rays. These come from radioactive decay, nuclear reactions, and the most violent events in the universe. Supernovas produce gamma rays. Black holes produce them. They carry so much energy that a single gamma ray photon can break apart atoms. All of these are the same thing, electromagnetic waves. The only difference is frequency and wavelength. Change the frequency, and you change everything about how the wave behaves and what it can do. But the fundamental nature stays the same. Electric and magnetic fields dancing together, moving through space at the speed of light. Your radio picks up one frequency. Your eyes pick up another. Your skin feels another. Each receiver is tuned to a different part of the spectrum, but the spectrum itself is continuous. There's no real boundary between microwave and infrared, between visible and ultraviolet. The divisions are human categories imposed on a smooth gradient of frequencies. The universe produces electromagnetic waves at every possible frequency. Stars emit them, atoms emit them, lightning emits them. Every time a charged particle accelerates, it produces electromagnetic waves. The universe is full of them, overlapping, passing through each other, filling space with oscillating fields. Right now, you're bathed in electromagnetic waves of every frequency. Most pass through you unnoticed. A few are absorbed by your skin as heat. A tiny fraction hits your retina and creates vision. Your body is constantly interacting with invisible waves, sorting them by frequency, responding to some, ignoring others. The Earth itself is wrapped in electromagnetic fields. The planet's molten iron core generates a magnetic field that extends thousands of miles into space. This field deflects most of the charged particles streaming from the sun. Without it, solar wind would strip away our atmosphere. The magnetic field is a shield, and it's generated by molten metal moving deep beneath your feet. When two waves meet, they don't bounce off each other. They pass through. But while they overlap, they combine. Their amplitudes add together. Where two crests meet, you get a higher crest. Where two troughs meet, you get a deeper trough. Where a crest meets a trough, they cancel out. This is called interference, and it creates some of the most beautiful patterns in nature. Drop two pebbles into still water. Each creates expanding circles of waves. Where the circles cross, you see a pattern. Some spots have large waves. Some spots are calm. The pattern holds steady, while the waves keep moving through it. The calm spots stay calm. The rough spots stay rough. It looks like magic, but it's just mathematics. The waves are adding and subtracting as they pass through each other. Light does this too. Shine two laser beams so they cross, and you'll see bright and dark bands where the light interferes with itself. The bright bands are where two crests meet and add together. The dark bands are where a crest meets a trough and they cancel out. Light plus light can equal darkness if the waves arrive out of step. This is how noise-cancelling headphones work. They listen to the sound around you, then produce a sound wave that's the exact opposite. Crest matches trough. Trough matches crest. The two waves cancel out, and you hear silence. Not because the sound is blocked, but because it's cancelled. The waves are still there, still moving through air, but their combined amplitude is 0. Ocean waves create interference patterns too, though they're harder to see because the ocean has so many waves of different frequencies moving in different directions. But sometimes, in certain conditions, the patterns become obvious. Cross seas happen when two wave systems meet at an angle. You get a checkerboard pattern on the ocean surface. It's beautiful from above, but dangerous for boats. The waves can come from unexpected directions, creating confused seas that are hard to navigate. The pattern in oil slicks on water comes from interference. The thin layer of oil reflects light from both its top surface and its bottom surface. The light waves reflected from the bottom have to travel slightly farther. That extra distance means they arrive out of step with the waves reflected from the top. For some colors, the waves add together and you see that color bright. For other colors, they cancel out. The result is the swirling rainbow pattern you see in oil or soap bubbles. The color depends on the thickness of the oil. Change the thickness by a tiny amount, and different colors cancel out or reinforce. That's why the patterns swirl and shift. Slight changes in thickness, too small to see directly, show up as dramatic color changes because of interference. Your ears hear interference as beats. Play two notes that are almost the same pitch, and you'll hear the volume rise and fall rhythmically. The waves are going in and out of phase with each other. When they align, the sound gets louder. When they oppose, it gets quieter. The beats happen at a frequency equal to the difference between the two notes. Play a 440 Hz note and a 442 Hz note together, and you'll hear beats at 2 Hz, 2 pulses per second. Musicians use this to tune instruments. When two strings are perfectly in tune, the beats disappear. The waves stay in step, and the sound is smooth. The moment they drift out of tune, beats appear. The musician adjusts until the beats slow down and stop. It's interference made audible, a tool for detecting tiny frequency differences. Interference happens with all waves. Sound waves, light waves, water waves. The mathematics is the same. Waves pass through each other. Their amplitudes add together according to simple rules, and patterns emerge. Sometimes the patterns are beautiful. Sometimes they're useful. Always, they reveal the wave nature of whatever is moving. Everything has a natural frequency, a frequency at which it wants to vibrate. Push something at its natural frequency, and the vibrations build. Energy accumulates. Small pushes add up to large movements. This is resonance. A child on a swing demonstrates it perfectly. The swing has a natural frequency determined by its length. Push at random times, and the swing barely moves. Push in rhythm with its natural frequency, and the swing goes higher with each push. You're adding energy at exactly the right time. The timing matters more than the force. Wine glasses have natural frequencies too. Tap a glass and it rings. That ring is the glass vibrating at its natural frequency. The shape and size of the glass determine the pitch. Sing that same pitch loudly enough, and the glass absorbs the sound energy. It starts vibrating. If the sound is loud enough and sustained enough, the vibrations can grow until the glass shatters. Sound waves destroying solid matter through resonance. Bridges can resonate. The Tacoma Narrows Bridge famously collapsed in 1940 when wind created vibrations at the bridge's natural frequency. The bridge began to twist and oscillate wildly. The oscillations grew larger. Eventually, the structure tore itself apart. Engineers now design bridges to avoid resonance frequencies or to dampen vibrations before they can build. Your body has resonance frequencies. Most are in the infrasound range, below what you can hear. Strong infrasound at the right frequency can make your organs vibrate. This can cause nausea, disorientation, panic. Some researchers think certain haunted places might have infrasound from wind or machinery, causing people to feel uneasy without knowing why. Their bodies are responding to vibrations they can't consciously hear. Musical instruments are designed around resonance. The body of a guitar is shaped to resonate at the frequencies of the strings. When you pluck a string, the body vibrates in sympathy. The vibrating wood moves more air than the thin string alone could. That's why an acoustic guitar is louder than an unplugged electric guitar. The wooden body resonates and amplifies. Your voice uses resonance too. Your vocal cords create a buzz of various frequencies. Your throat, mouth, and nasal cavities act as resonance chambers. They amplify certain frequencies and dampen others. Change the shape of these spaces, and you change which frequencies resonate. That's how you make different vowel sounds. The source is the same buzzing vocal cords, but the resonance pattern changes. Radio receivers use resonance to pick stations. The receiver contains a circuit that resonates at a specific frequency. Turn the dial and you change the resonant frequency. When it matches a radio station's broadcast frequency, that signal resonates in the circuit and gets amplified. All the other frequencies present in the air around you don't resonate. They pass through without being amplified. That's how your radio can pick one station out of hundreds broadcasting simultaneously. MRI machines use resonance to see inside your body. They create a powerful magnetic field. This field makes hydrogen atoms in your body align. Then, a radio wave pulse hits those atoms at their resonance frequency. The atoms absorb the energy. When the pulse ends, they release that energy as they relax back to alignment. The machine detects this released energy. Different tissues release energy at slightly different rates. That's how the machine builds an image of your internal structures. Resonance is why opera singers can make you feel sound in your chest. They're producing frequencies that resonate in your chest cavity. Your sternum vibrates. Your ribs vibrate. You feel the sound as much as hear it. The same happens with very low bass notes. Below a certain frequency, you stop hearing the sound clearly, but you feel it as a physical vibration in your body. The Earth has resonance frequencies too. Lightning strikes create electromagnetic waves that circle the globe. Some of these waves have wavelengths that match the circumference of the Earth. They resonate, building up in amplitude. The space between the Earth's surface and the ionosphere acts like a resonance chamber for extremely low frequency electromagnetic waves. These are called Schumann resonances, and they pulse at about 7.83 Hz, a slow throb that's been constant for millions of years. Earthquakes send waves through the entire planet. 3 main types, each moving differently, each telling geologists something about the Earth's interior. P waves are pressure waves. They work like sound waves, compressing and expanding rock as they travel. They move fast, about 15,000 miles per hour through the crust. They can travel through any material, solid or liquid. When an earthquake happens, P waves arrive first. That's what the P stands for, primary. S waves are shear waves. They move rock side to side, perpendicular to their direction of travel. They're slower than P waves, about 10,000 miles per hour in the crust, but they can't travel through liquids. This is important. This is how we know the Earth's outer core is liquid. S waves from earthquakes on one side of the planet never reach the other side. They're absorbed by the liquid outer core. Their absence creates a shadow zone where no S waves arrive. Surface waves travel along the Earth's crust. They're the slowest but often the most destructive. They move the ground up and down and side to side. Buildings can handle vertical motion fairly well. Side-to-side motion is harder. That's what topples structures during major earthquakes. Seismologists use these waves like doctors use X-rays. The waves travel through the Earth and arrive at sensors all over the world. The timing tells you how far they've traveled. The path they took tells you what they moved through. Waves traveling through denser material move faster. Waves encountering liquid slow down or stop entirely. By studying thousands of earthquakes, scientists have mapped the Earth's interior. They found the solid inner core, the liquid outer core, the thick mantle, and the thin crust we live on. They've identified layer boundaries by seeing how waves speed up or slow down when they cross those boundaries. The entire picture of Earth's structure comes from watching waves move through rock. Some waves travel around the world multiple times before fading. A large earthquake sends energy through the entire planet. The waves reflect off boundaries between layers. They refract as they pass through materials of different densities. They circle the globe, arriving at distant sensors from multiple directions. Geologists record these arrivals and work backward to figure out what path the waves took, what they passed through, how the interior must be structured to produce those arrival patterns. The Earth rings like a bell after major earthquakes. The whole planet vibrates at extremely low frequencies. These vibrations can continue for days after a large quake, slowly dissipating as the energy spreads out. The frequency of these vibrations depends on the size and elasticity of the entire Earth. By measuring them precisely, scientists can determine properties of the deep interior that no drill could ever reach. Earthquake waves have revealed something else surprising. The Earth's interior isn't uniform. There are variations in density and composition. Some parts of the mantle are slightly hotter, some slightly cooler. These variations affect how fast waves travel through them. The result is a three-dimensional map of the mantle, showing plumes of hot rock rising from the core mantle boundary, and slabs of cold rock sinking down from the surface where tectonic plates dive beneath each other. All of this from waves. Energy released by grinding tectonic plates, traveling through rock, recorded by sensitive instruments, analyzed by scientists trying to understand the planet beneath their feet. The waves carry information. The challenge is learning how to read it. Every earthquake is an experiment. Nature is sending waves through the Earth, and scientists are recording them, learning a little more about what's down there each time. The picture gets clearer with each quake. The uncertainty shrinks. The model of the Earth's interior becomes more refined. Right now, waves are traveling through the rock beneath you. The Earth is never completely still. Small earthquakes happen constantly. Tectonic plates grind against each other. Magma moves. Every movement sends waves. The planet is always vibrating, always transmitting. Waves carry energy from one place to another without moving matter. This is their fundamental purpose. Energy transport without mass transport. It's efficient. It's elegant. It's how nature moves things that need moving without physically pushing matter across space. The sun proves this every day. Energy created in the core must reach the surface, 400,000 miles away. It can't flow through the sun like water through a pipe. The interior is too dense. Instead, energy moves as radiation. Photons bounce from atom to atom, getting absorbed and re-emitted millions of times. Each photon takes a random walk through the solar interior. The journey that could be traveled in 2 seconds at the speed of light actually takes tens of thousands of years because of all the bouncing. Eventually, the energy reaches the surface. It launches into space as electromagnetic waves. 8 minutes later, it arrives at Earth. The energy that started as fusion in the sun's core is now warming your skin, powering photosynthesis, driving weather patterns, creating wind and waves. All of that energy traveled as waves. No mass moved from the sun to Earth. The photons that left the sun's surface didn't exist in the sun's core. They were created at the surface by hot atoms emitting light. But the energy is the same energy. It just changed forms and carriers during the journey. Ocean waves carry tremendous energy. A single large wave can contain enough energy to power a city block for a day. That energy came from wind, which got its energy from solar heating, which came from the sun's fusion. The energy flowed from process to process, each time being carried by waves. Heat waves from the sun to Earth, pressure waves in the atmosphere creating wind, surface waves on the ocean carrying the wind's energy toward shore. When waves hit the shore, their energy has to go somewhere. Some of it becomes sound, some becomes heat. Most goes into moving water and sand. The endless pounding of waves shapes coastlines. Cliffs erode, beaches form, rock turns to sand, all powered by wave energy that started as fusion reactions in the sun's core. Engineers have tried to harvest wave energy. The idea is simple. Waves contain power. Convert that power to electricity. The execution is harder. Waves are irregular. They come from different directions. They vary in size and frequency. Building something that can survive storms while efficiently capturing energy from gentle waves is a challenge that's still being solved. But the energy is there. Some estimates suggest ocean waves could provide a significant fraction of human energy needs if we could capture them efficiently. The waves don't care if we use them or not. They'll keep carrying energy from mid-ocean to shore regardless. That energy will keep shaping coastlines, creating sounds, warming beaches. It's there for the taking if we develop the technology. Electromagnetic waves carry energy too, in a different way. A radio transmission doesn't carry much energy. The waves that bring music to your radio can't heat your skin or move objects, but they carry information, which in some ways is more valuable than raw energy. Information about stock prices, instructions for landing aircraft, voices of people thousands of miles away, all encoded in patterns of electromagnetic waves. Your cell phone converts your voice to electromagnetic waves. Those waves travel to a cell tower. The tower rebroadcasts them. They reach another phone. That phone converts the waves back to sound. Your voice never travels. Your vocal cords vibrate air in your throat. That's as far as the actual sound goes. Everything else is electromagnetic waves carrying a pattern that represents your voice. The pattern arrives at the other phone and gets converted back to sound waves that vibrate air in someone else's ear. Energy flows through the world in waves. Light from the sun, sound from voices, radio waves carrying data, ocean swells carrying momentum from distant storms, earthquake waves carrying information about the planet's interior. All of it is energy in motion, following the same basic rules, subject to the same mathematics. The universe runs on waves. They're the mechanism for energy transport at every scale. From quantum fields to ocean swells, from light across cosmic distances to sound across a room, waves carry what needs carrying. They ask nothing. They take nothing. They simply move energy from where it is to where it needs to be. Matter is made of waves too. This fact is so strange that it took decades for physicists to accept it. But experiments kept showing it. Particles of matter behave like waves. Not just behave like them, they are them. Electrons were thought to be particles, tiny bits of matter orbiting atomic nuclei. Then experiments showed that electrons create interference patterns just like light waves. Fire electrons one at a time through a double slit, and they don't behave like bullets. They behave like waves, creating bright and dark bands on a detector screen. Each electron somehow interferes with itself, as if it's a wave passing through both slits at once. The same happens with atoms, with molecules, even with small viruses. Everything exhibits wave properties when tested correctly. The wave nature of matter is fundamental. Particles don't have a position until they're measured. Before measurement, they exist as waves of probability, spread out in space. The wave describes all the places the particle might be. Measure it, and the wave collapses. The particle appears in one location. This is called wave-particle duality, though that makes it sound like things are sometimes particles and sometimes waves. Really, everything is always waves. We just perceive them as particles when we look closely enough. The wave nature is always there, underlying everything. Your body is made of atoms. Each atom's electrons are waves. The electrons don't orbit the nucleus like planets around the sun. They exist as standing waves around the nucleus, patterns of probability that happen to have wavelengths matching the size of the atom. The shape of these waves determines the atom's properties, how it bonds with other atoms, what colors of light it absorbs. Everything about chemistry comes from the wave nature of electrons. The wavelength of matter depends on its momentum. Fast-moving particles have shorter wavelengths. Slow particles have longer wavelengths. Massive particles have shorter wavelengths than light particles moving at the same speed. This is why you don't notice the wave nature of everyday objects. A baseball in flight has a wavelength trillions of times smaller than an atomic nucleus. The wave is there, but it's so small it has no practical effect. But electrons are light enough and small enough that their wave nature matters. The wavelength of an electron in an atom is comparable to the size of the atom itself. The wave properties dominate. That's why atoms behave quantum mechanically. That's why electrons exist in discrete energy levels instead of any possible orbit. Only certain wavelengths fit around the nucleus. Only certain standing waves are stable. This wave nature explains why atoms are stable. If electrons were classical particles, they would spiral into the nucleus. Moving charges radiate energy. They would lose energy and crash. But electrons as waves don't radiate when they're in a stable pattern. The wave isn't moving. It's a standing wave, like the vibration pattern of a drumhead. It persists without losing energy. Light behaves the same way. Photons are particles, but they're also waves. They interfere, they diffract, they create patterns that only waves can create. Einstein explained this by saying light comes in packets of wave energy. Each photon is a particle of light, but each photon's properties are determined by its wavelength and frequency, particle and wave at once. This duality is at the heart of quantum mechanics, the theory that describes how the universe works at the smallest scales. Everything is waves. Those waves tell you probabilities, where a particle might be, what energy it might have. The wave function contains all possible states. Measurement forces the wave to choose one state and collapse into it. The implications are vast and strange. Particles can tunnel through barriers by existing as waves on both sides simultaneously. Atoms can be in two places at once, as long as you don't look. The act of looking changes things. Measurement collapses the wave. The universe, at its smallest scale, is probabilistic, not deterministic. Cause and effect break down. Only probabilities remain, encoded in waves that fill space, until something forces them to become real. Your body contains trillions of atoms. Each atom's electrons are waves. Those waves interact. They overlap. They create the chemical bonds that make molecules. Those molecules make cells. Those cells make you. At the deepest level, you are patterns of waves, stable configurations of quantum fields, probability distributions that have collapsed into flesh and blood and thought. You are waves that learned to think about waves. Matter contemplating its own wave nature. The universe looking at itself through eyes made of the same quantum fields it's trying to understand. When a wave hits a boundary between two materials, part of it reflects and part continues through. The angle and speed change, but the wave keeps going. This is refraction, and it happens with every wave at every boundary. Light refracts when it enters water. That's why a stick looks bent when you dip it in a lake. The light reflecting off the underwater part of the stick changes direction as it leaves the water. Your eye traces that light back in a straight line and sees the stick in the wrong place. The stick is straight. The light path is bent. Water refracts light because light moves slower in water than in air. When a wave enters a slower medium at an angle, the part that enters first slows down, while the rest is still moving fast. The wave front pivots, changing direction, like a car driving from pavement onto sand at an angle. The wheel that hits the sand first slows down. The car turns. This is how lenses work. Glass slows light. Shape the glass correctly, and you can focus light to a point. Your eye uses a lens to focus light on your retina. The lens in your eye can change shape, letting you focus on objects at different distances. Camera lenses do the same thing, using precisely shaped glass to bend light rays until they converge. Mirages happen because of refraction too. Hot air near the ground is less dense than cool air above it. Light moves slightly faster through the hot air. As light from the sky travels downward, it speeds up in the layers near the ground. The light path curves upward. You see sky where ground should be. Your brain interprets this as water reflecting the sky. That's a mirage, not an illusion. Real light taking a curved path through air of varying density. Sound refracts through layers of water at different temperatures. Submarines use this. Cold water refracts sound differently than warm water. A submarine can hide in a layer of cold water beneath warm water. Sonar from above gets refracted away. The submarine becomes invisible to sound. Whales probably know about these layers too. They can use them to project their songs farther, or to hide from predators. Ocean waves refract when they approach shallow water. The part of the wave in shallow water slows down. The part still in deep water keeps moving at full speed. The wave front pivots, bending to become more parallel to the shore. That's why waves usually hit beaches head-on, even when they approach from an angle far out at sea. Reflection is simpler. A wave hits a boundary and bounces back. Light reflects off mirrors. Sound reflects off walls, creating echoes. Ocean waves reflect off harbour walls and cliffs. The angle of reflection equals the angle of approach. This is one of the fundamental laws of waves. Bats use reflection to see. They emit high-frequency sound and listen for echoes. The echo tells them the distance to objects and the object's shapes. A flat surface produces a strong echo. A textured surface scatters sound in many directions, producing a weaker echo. Rough surfaces versus smooth ones. The bat's brain interprets these differences as a three-dimensional map of the world. Dolphins do the same thing underwater. Their echolocation is so precise, they can detect a coin-sized object buried in sand from several feet away. They can tell the difference between different types of metal based on how they reflect sound. They're seeing with sound, using the reflection of waves to build images. Your voice, reflecting in a room, tells you about the room. A small room with hard walls produces quick, sharp echoes. A large room with soft surfaces produces softer, delayed echoes. Concert halls are designed with careful attention to how sound reflects. Too much reflection and the sound becomes muddy. Too little and it feels dead. The right amount creates richness, warmth, depth. Electromagnetic waves reflect too. Radar works by reflecting radio waves off objects. The time delay tells you the distance. Weather radar reflects off raindrops. Air traffic control. Radar reflects off aircraft. The same principle as bat echolocation, just using electromagnetic waves instead of sound. Every boundary is an opportunity for waves to change direction, to split, to continue in new paths while carrying the same energy. The waves don't choose. They simply follow rules written into the nature of space and materials. Standing waves don't travel. They vibrate in place, creating patterns that hold steady while energy sloshes back and forth. You see them when you pluck a guitar string. The string vibrates, but certain points along its length don't move at all. These are nodes. Between the nodes are antinodes, points of maximum movement. The string can only vibrate at certain frequencies. Frequencies where the wave pattern fits exactly on the string's length. The lowest frequency is when the string vibrates as one big arc. This is the fundamental frequency, the pitch you hear most clearly. But the string also vibrates in halves, thirds, quarters. All these patterns happen simultaneously. They're called harmonics. The fundamental and harmonics together create the string's timbre, the quality that makes a guitar sound different from a piano, even when both play the same note. Same fundamental frequency, different mix of harmonics. Your ear hears the full combination, and your brain recognizes the instrument. Every instrument creates standing waves. In a flute, air vibrates inside the tube. In a drum, the membrane vibrates. In your voice, air vibrates in your throat and mouth. The shape and size determine which frequencies fit, which harmonics are strongest. That's why every instrument has its own voice. Organ pipes produce standing waves in air columns. Close both ends and you get one set of harmonics. Open one end and you get a different set. The longest organ pipes are over 30 feet tall. They produce notes so low you feel them more than hear them. The wavelength of those notes is longer than the pipes themselves. The pipe is creating standing waves of enormous wavelength. Standing waves appear in water too. Slosh water in a bathtub, and you can create patterns where water piles up at the ends while staying low in the middle. The natural frequency depends on the tub's length and the water depth. Push at that frequency and the wave builds. The water doesn't flow from one end to the other. It rises and falls in a standing pattern. Lakes can resonate this way. Wind or earthquakes can set up standing waves called seaches. The entire lake surface tilts, high at one end, low at the other, then reverses. The period can be minutes or hours, depending on the lake's size. The water doesn't travel the length of the lake. It rocks back and forth, creating a standing wave on a massive scale. The sun vibrates with standing waves. Its entire surface pulses in complex patterns, with periods of about 5 minutes. These vibrations are pressure waves trapped inside the sun, bouncing between the surface and the core. By studying these standing wave patterns, scientists can determine conditions deep in the sun's interior. It's like listening to a bell and working backward to figure out its shape and composition. Standing waves require boundaries, something to reflect the wave back on itself, so it can interfere with incoming waves. When waves traveling in opposite directions overlap just right, they create points that never move and points that move with double amplitude. The nodes and antinodes of a standing wave. Your ears can create standing waves in certain conditions. Sound in an enclosed space can reflect back and forth until certain frequencies build up. This is why some rooms have annoying resonances. A particular note sounds much louder than others. The room's dimensions create standing wave patterns at specific frequencies. Electromagnetic standing waves exist inside microwave ovens. The microwaves bounce off the metal walls and create standing wave patterns, hot spots and cold spots. That's why microwave ovens have turntables. They rotate the food through the hot and cold spots, so heating is more even. Without rotation, the standing wave pattern would cook some parts while leaving others cold. Atoms contain standing waves. The electron waves we talked about earlier are standing waves around the nucleus. Only certain patterns fit. Only certain wavelengths match the space available. This is why electrons exist in discrete energy levels. The standing wave must complete a whole number of cycles around the nucleus. Half a wave doesn't work. 3.5 waves doesn't work. Only whole numbers. Only standing wave patterns that close on themselves. This is the foundation of quantum mechanics. Standing waves of matter, creating the stable patterns we call atoms. Energy quantized because only certain standing wave patterns are stable. The entire periodic table exists because electrons form standing waves around nuclei. Tsunamis are not like regular ocean waves. They're caused by sudden movements of the seafloor. Earthquakes, underwater landslides, volcanic eruptions. Something displaces a huge volume of water all at once. That displacement becomes a wave that travels across entire ocean basins. In deep water, a tsunami is barely noticeable. The wave height might be only a few feet, but the wavelength is enormous, hundreds of miles from crest to crest. The wave travels at hundreds of miles per hour. The entire ocean depth participates in the wave motion. Unlike surface waves, where only the top layer moves, a tsunami moves water from surface to seafloor. As the wave approaches shore, the seafloor rises. The wave slows down, but the energy has to go somewhere. The wavelength shortens. The amplitude grows. A 3-foot wave in the open ocean becomes a 30-foot wave at the coast. The water doesn't arrive as a breaking wave like surfers ride. It arrives as a rising of the entire sea level, a surge that keeps coming, pushing inland, overwhelming everything in its path. Before the wave arrives, the water often recedes. The trough of the wave reaches shore first. The ocean pulls back hundreds of feet, exposing seafloor that's normally underwater. This is the warning sign. When you see the ocean retreat like that, you have minutes to get to high ground. The wave is coming. The first wave is rarely the largest. Tsunamis come in sets. Multiple waves, each traveling at high speed, arriving minutes or hours apart. The second or third wave is often the tallest. People sometimes return to the coast after the first wave, thinking it's over. Then a larger wave arrives. The 2004 Indian Ocean tsunami traveled across the entire ocean. The earthquake that caused it displaced trillions of gallons of water. The energy spread outward in all directions at 500 miles per hour. Coastal areas thousands of miles from the earthquake were hit hours later. The wave traveled farther than commercial jets could fly in the same time. The energy in a tsunami is staggering. A single wave can carry the kinetic energy of multiple nuclear weapons. That energy, spread over hundreds of miles of wavelength, doesn't seem like much in deep water. Concentrated by shallow coastal topography, it becomes devastating. Warning systems now track tsunamis using seafloor pressure sensors. A pressure change of a few inches in water, thousands of feet deep, signals a tsunami passing overhead. The sensors radio the data to satellites. Computers calculate the wave's speed and direction. Warnings go out to coastal areas in its path. Minutes or hours of warning time, enough to evacuate if people respond immediately. The wave doesn't stop at the first shoreline it hits. It can refract around islands. It can reflect off coastal features and change direction. Harbour shapes can focus tsunami energy, making waves higher in some locations. 2 hours after a tsunami hits one coast, reflected waves can hit another coast from an unexpected direction. Tsunami waves can travel thousands of miles from their source and still cause damage. The 2011 Japan tsunami sent waves across the Pacific. Harbors in California and Oregon saw boats torn from moorings. A man in Oregon was swept into the ocean and drowned. The wave had traveled 5,000 miles, crossed an entire ocean, and still carried enough energy to kill. The ocean remembers these events in sediment. Tsunami deposits of sand and shells are found inland, above normal high tide marks. By studying these deposits, scientists have found evidence of past tsunamis, events from centuries ago, before written records. The sediment layers tell stories of waves that struck coasts long before anyone was there to record them. Every wave carries energy. Most waves carry small amounts, create gentle effects, cause little change. But when enormous energy is released suddenly underwater, when the entire ocean depth begins to move, the waves that result carry destruction across entire ocean basins. The same mathematics that describes ripples in a puddle describes these monster waves. Just different scales, different energies, different consequences. Your brain runs on waves. Electrical signals pulse through neurons, creating rhythms that sweep across the cortex. These brainwaves can be measured, categorized, linked to different states of consciousness. Delta waves are the slowest. They pulse 1 to 4 times per second. You produce them during deep sleep, the kind of sleep where you're completely unconscious, not dreaming, not easily awakened. Delta waves are large and slow, like ocean swells moving through your brain. Theta waves are slightly faster, 4 to 8 pulses per second. They appear during light sleep and during deep meditation, that drowsy state just before you fall asleep fully. Theta waves are associated with memory formation and emotional processing. Your brain is working even when you're not aware of it. Alpha waves run 8 to 12 times per second. They show up when you're awake but relaxed. Close your eyes and alpha waves strengthen. Open them, and alpha waves diminish. They seem to be the brain's idle state, awake but not focused on anything particular. Beta waves are faster still, 12 to 30 pulses per second. These are your waking, thinking, active brain waves. When you're focused on a task, solving a problem, engaged in conversation, beta waves dominate. They're the signature of an alert mind. Gamma waves are the fastest measured brain waves, 30 to 100 pulses per second. They appear during intense focus, during moments of insight, during peak mental performance. What they do exactly isn't fully understood, but they seem to correlate with binding together information from different brain regions. These aren't 5 separate systems. Your brain produces all these frequencies simultaneously. The mix changes depending on what you're doing. Deep sleep shifts the balance toward delta. Meditation brings more theta. Active thinking increases beta. The brain is like an orchestra with multiple sections, playing different rhythms that combine into a coherent whole. The waves aren't just local. They sweep across large areas of the cortex in coordinated patterns. During sleep, delta waves roll from front to back across your brain. These traveling waves seem to help consolidate memories, moving information from temporary storage into long-term memory. When you focus attention, beta waves in different brain regions synchronize. The synchronization allows those regions to communicate effectively. Areas processing visual information sync with areas planning movement. You see an object and reach for it smoothly because the relevant brain areas are oscillating in phase, sharing information efficiently. The waves can be disrupted. Epileptic seizures happen when neurons fire too synchronously. Instead of normal rhythms, huge waves of activity sweep through the brain. Consciousness is lost. The body convulses. The wave passes, and normal rhythms return, but the person has no memory of the seizure. The normal brainwave patterns were temporarily overwritten by a massive synchronized firing. Sleep disorders often involve abnormal brainwave patterns. People with insomnia show brainwave patterns that don't transition properly from waking to sleeping states. Beta waves persist when delta should dominate. The brain doesn't shift gears. Sleep doesn't come. Brain-computer interfaces read these waves. Electrodes on the scalp detect the combined electrical activity of millions of neurons. Software analyzes the patterns and translates them into commands. Think about moving your hand and beta waves in your motor cortex change. The computer detects this change and moves a cursor. It's crude compared to actual movement, but it works. The waves carry information that machines can read. Meditation traditions have talked about altering consciousness for thousands of years. Modern neuroscience shows they were right. Experienced meditators can voluntarily increase theta and alpha waves. They can create brainwave patterns normally seen only during sleep while remaining fully awake. The subjective experience of meditation correlates with objective changes in brainwave patterns. Your mental state is, in part, a matter of which waves dominate in your brain. Sleep, waking, focus, relaxation, all characterized by different rhythms, different frequencies of neuronal firing, different patterns of waves flowing through the tissue of your cortex. The brain is an electrical organ. Its activity creates fields, generates rhythms, produces waves that can be measured and, to some extent, controlled. Gravitational waves are ripples in space-time itself, not waves traveling through space, but waves of space. they stretch and compress the fabric of reality as they pass. Einstein predicted them a century ago. His equations showed that accelerating massive objects should create waves that propagate at light speed, but he thought they'd be too weak to ever detect. The distortion they cause is unimaginably small. He was right about the weakness. A gravitational wave passing through Earth stretches it by less than the width of an atomic nucleus. Detecting something that small is like measuring the distance to the nearest star with precision better than the width of a human hair. But scientists built detectors anyway. LIGO, 2 massive facilities in Louisiana and Washington. Each has 2 arms stretching 2.5 miles in an L shape. Laser beams bounce between mirrors at the ends of the arms. The beams interfere, and any change in the arm lengths shows up as a change in the interference pattern. In 2015, both detectors simultaneously recorded a signal, a chirp lasting a fraction of a second. The signal matched what theory predicted for 2 black holes spiraling together and merging. The black holes were each 30 times the mass of the Sun. They orbited each other faster and faster, emitting gravitational waves. As they lost energy to the waves, they spiraled closer. Finally, they merged in a violent collision that released more power than all the stars in the observable universe combined. That power was released as gravitational waves, ripples in space-time that spread outward at light speed. The waves traveled for over 1 billion years, crossing space while the universe expanded, while stars formed and died, while Earth went from molten rock to a planet with life. The waves finally reached Earth on September 14th, 2015, and slightly compressed and stretched the LIGO detectors for a fraction of a second. Since then, dozens of similar events have been detected. Merging black holes of various masses, merging neutron stars. Each event releases a characteristic signal. The frequency increases as the objects spiral closer. The amplitude grows as they accelerate. The signal cuts off when they merge. The shape of the signal tells scientists the masses of the objects, their spins, their distance from Earth. Gravitational waves are fundamentally different from other waves. Electromagnetic waves are oscillations of fields. Sound waves are oscillations of pressure. Gravitational waves are oscillations of space-time geometry. They change the shape of space itself. They stretch distance in one direction while compressing it in the perpendicular direction. Space becomes distorted, then returns to normal, then distorts again as the wave passes. Nothing can block gravitational waves. They pass through everything: Earth, the Sun, giant planets. Gravitational waves don't interact with matter the way light or sound does. They interact with space-time, which means they interact with everything equally. Matter just goes along for the ride as space stretches and compresses. The waves carry energy away from their source. This isn't obvious. They're distortions of empty space. But the distortions represent energy. When black holes merge, about 5% of their total mass is converted to gravitational wave energy. Mass becomes energy in the form of space-time ripples. Einstein's ERMC node, in a form he might not have fully anticipated. Binary star systems should emit gravitational waves. As they orbit, they accelerate. Accelerating masses produce waves. The waves carry away energy. The orbit should shrink. This has been measured. The Hulse-Taylor binary pulsar has been observed for decades. Its orbit is shrinking at exactly the rate predicted by gravitational wave emission. The stars are spiraling together, losing energy to waves we can't detect directly, but can measure through their effect. Gravitational waves let us observe events that produce no light. Black hole mergers happen in darkness. No light escapes a black hole. But gravitational waves carry information about what happens when they collide. For the first time, humanity can detect events that are completely invisible to telescopes. The universe is full of gravitational waves, merging black holes, merging neutron stars, possibly other exotic events we haven't imagined yet. The waves pass through Earth constantly, too weak to feel, barely strong enough to detect with our best instruments. Space ripples with the violence of distant collisions. We're only beginning to listen to this new channel of information. The universe is speaking in gravitational waves. We're learning its language. Waves shaped how life evolved. Organisms that could detect waves had advantages. They could sense danger, find food, navigate, communicate. Evolution favored wave detection. Eyes evolved to detect electromagnetic waves. Ears evolved to detect pressure waves. Lateral lines in fish detect water waves. Electroreception in sharks detects electrical waves. Vision started simple. Light-sensitive spots on early organisms. A patch of cells that could tell light from dark. This gave advantage. Move toward light, where photosynthesis happens. Move away from shadows where predators lurk. Simple detection became more refined over hundreds of millions of years. The eye evolved multiple times independently, in different lineages. Octopuses have camera-like eyes similar to ours, but they evolved separately. The similarity is convergence. Good designs emerge independently because they solve the same problem. Focusing light onto a detector surface is an effective way to see. Evolution discovered this solution multiple times. Your eye can detect a single photon, the minimum possible light. One quantum of electromagnetic wave. The chemical in your retina cells changes shape when hit by a photon. That shape change triggers a cascade that sends a signal to your brain. One photon is enough. Your eye is operating at the quantum limit of sensitivity. Hearing evolved from touch. Simple hair cells that detect vibration. These cells became specialized, sensitive to specific frequencies. In your inner ear, hair cells of different lengths respond to different pitches. Long cells respond to low frequencies, short cells to high frequencies. Your cochlea sorts sound by frequency, creating a map of pitch along its spiral structure. Bats evolved echolocation independently from dolphins. Different lineages, same solution. Emit sound, listen for echoes. Build a picture of the world from the returning waves. The mathematics of echoes is the same whether you're a bat in air or a dolphin in water. Evolution found the same answer twice. Some species detect waves, humans can't. Snakes sense infrared. Pits near their eyes detect heat signatures of prey. They're seeing in infrared, detecting electromagnetic waves too long for human eyes. Bees see ultraviolet. Flowers have patterns visible only in UV, guides that point to nectar. The flower advertises to its pollinator, using wavelengths we can't perceive. Electric fish generate and detect electrical fields. They navigate murky water by sensing distortions in their self-generated field. Objects conduct electricity differently than water. The distortion reveals their location. It's seeing through electrical waves, a sense completely foreign to human experience. Birds might detect Earth's magnetic field. How exactly is debated, but some evidence suggests molecules in their eyes respond to magnetic fields. They might literally see the magnetic field lines as patterns of color or brightness overlaid on their normal vision. They navigate by following lines only they can perceive. Whales and elephants communicate in infrasound, frequencies below human hearing. Their calls travel enormous distances. Whales coordinate across hundreds of miles of ocean. Elephants coordinate across miles of savanna. They're using the long-distance propagation properties of low-frequency sound waves. Humans standing nearby wouldn't hear the call, but other elephants 20 miles away receive the message clearly. Plants respond to light waves with exquisite sensitivity. Different wavelengths trigger different responses. Red light triggers flowering in some species. Blue light controls growth direction. Plants don't have eyes, but they have photoreceptors throughout their tissues. They sense light quality, light direction, light duration. They track the sun across the sky. They grow toward light sources, all by detecting and responding to electromagnetic waves. Evolution discovered wave detection hundreds of millions of years ago and has been refining it ever since. Every animal, every plant, every organism uses waves to interact with the world. The ability to sense and interpret waves is fundamental to life. Without it, organisms are deaf and blind, cut off from information about their environment. With it, the world opens up. Predator and prey detect each other. Mates find each other. Food sources are located. Navigation becomes possible, all through detection of various waves. The ocean's surface is never truly still. Even on the calmest day, ripples spread from tiny disturbances. A fish breaking the surface. An insect landing on the water. The impact of a raindrop. Each creates waves that spread outward in perfect circles, growing weaker as they expand, eventually dissipating into the random texture of the water's surface. These small disturbances create capillary waves, the smallest ocean waves, measured in millimeters. Surface tension dominates over gravity at this scale. The water behaves differently. The waves move fast despite their tiny size. They're the first to respond to wind. As breeze starts to blow, capillary waves appear instantly. The wind pushes on these small waves, and they grow into gravity waves. Now, gravity becomes the restoring force. The wave rises. Gravity pulls it back down. The wave falls below average level. Gravity pulls water back up. This creates oscillation. The wave persists, traveling across the water surface, carrying energy from the wind. Wind waves grow in three ways: longer duration of wind, longer distance over which wind blows, and higher wind speed. All three factors matter. A hurricane produces enormous waves because it has strong winds blowing over hundreds of miles for hours or days. The waves have time and distance to grow. The largest wind waves are about 60 feet from trough to crest in the open ocean. Larger waves are possible, but rare. Ships occasionally report rogue waves over 100 feet tall. These are statistical anomalies, moments when multiple wave trains align perfectly and their amplitudes add. The monster wave exists for minutes, then the components separate and it disappears. Waves travel in groups. The group velocity is slower than the individual wave velocity. Watch waves approaching shore, and you'll see something strange. Individual wave crests move through the group, appearing at the back, traveling forward through the group, and disappearing at the front. The group advances slowly, while the individual waves move faster through it. This happens because waves of different wavelengths travel at different speeds in deep water. Longer waves go faster. The group contains waves of slightly different wavelengths. They interfere, creating the pattern of wave packets with gaps between them. The packets move at the average speed, while individual crests move at the speed determined by their wavelength. As waves approach shore, everything changes. The seafloor begins to affect them. The wave feels the bottom when the water depth is less than half the wavelength. Friction slows the wave. The wavelength shortens. The wave gets steeper. The front of the wave is in shallower water than the back, so the back catches up. The wave steepens more. Eventually, the top outruns the bottom. The wave breaks. Different beach slopes create different breaking patterns. Steep beaches cause waves to plunge. The crest curls over and crashes down. Gentle slopes cause waves to spill. The crest gradually foams and tumbles. Very flat beaches cause waves to surge. They rise up but don't really break, just rush up the beach as a wall of water. Breaking waves release their energy. The water churns. Air gets mixed in. Foam appears. The energy becomes heat, sound, water, motion. The organized wave becomes chaotic turbulence. Then the water drains back down the beach, pulled by gravity, ready to be lifted by the next wave. The process is constant. Wind creates waves far out at sea. The waves travel for days or weeks. They refract as they approach shore. They break on beaches around the world. The energy that started as solar heating creating wind ends as the sound of surf on sand. The cycle never stops. Right now, waves are forming in mid-ocean, and waves are breaking on every coastline. The ocean breathes waves onto the shore, inhales them back out, breathes them in again. Seismic waves reveal the structure of Earth, but they've also revealed something unexpected about how the planet works. The mantle is solid, but it flows. Over thousands of years, rock deep underground moves like a very thick fluid. Seismic waves show this motion. Tomography is the technique, like a medical CT scan, but for the entire Earth. Waves from thousands of earthquakes, recorded at thousands of seismometer stations. The arrival times of these waves depend on what they passed through. Hot material transmits waves slower than cold material, denser material faster than lighter material. By analyzing all these arrival times together, scientists build a three-dimensional map. The map shows blobs of hot material rising from near the core. The blobs rise under mid-ocean ridges where new seafloor forms. They show slabs of cold material sinking where tectonic plates dive beneath each other. The pattern explains plate tectonics. The hot material rises, spreads out beneath the plates, cools and sinks. This convection cycle drives the plates. Continents ride on top of these convection currents like leaves on a stream. Over millions of years, continents drift across the planet's surface. The boundary between the mantle and core shows up clearly in seismic data. Waves abruptly slow down at this boundary. The jump in speed indicates a major change in material properties. The mantle is rock. The outer core is liquid iron. The change is dramatic. S-waves that travel through rock cannot travel through the liquid core. Their absence reveals the core's state. The inner core is solid, despite being hotter than the outer core. The pressure is so extreme that iron freezes even at temperatures of over 9,000 degrees Fahrenheit. Seismic waves traveling through the inner core move faster in one direction than others. This anisotropy reveals that the iron crystals are aligned. The inner core has structure. It's not a simple ball of iron, but organized crystals, possibly rotating at a slightly different rate than the rest of the planet. Waves have detected mountains at the core mantle boundary. ranges as tall as the Himalayas, but upside down, hanging from the bottom of the mantle into the core. These features show up as anomalies in wave travel times. Material piled up at this boundary must have different properties. Perhaps it's ancient seafloor that sank all the way to the bottom. Perhaps it's material that never fully mixed with the mantle. The waves detect it, but its composition remains mysterious. The very center of Earth is beyond direct reach. No drill can go that deep. The pressure and temperature are too extreme, but waves penetrate effortlessly. They carry information back to the surface. By studying the waves, scientists know more about the deep Earth than they do about some parts of the ocean floor. Waves provide access to places that are physically unreachable. Each large earthquake is an experiment. Energy released at one point, waves radiating out. The entire planet rings like a bell. Seismometers worldwide record the ringing. The data accumulates. The picture of Earth's interior becomes sharper. Features once invisible come into focus. The dynamic processes happening thousands of miles below your feet become visible through the waves they affect. The Earth is not static. The mantle churns. The core swirls. Material rises and falls over millions of years. All of this happens in darkness and silence, under pressures that would instantly crush any human-made probe. But waves pass through it all, collecting information, delivering it to instruments at the surface. The solid Earth reveals its secrets through the waves it transmits. Every sound you hear arrives as a pattern, not just a single frequency, but a blend of many frequencies arriving together. Your brain decodes these patterns instantly. A voice speaking, a car passing, wind in leaves. Each sound has a characteristic frequency spectrum, a signature pattern of which frequencies are present and how strong they are. Speech relies on complex patterns. Your vocal cords create a buzz of various frequencies. Your mouth and throat shape those frequencies. Different shapes emphasize different frequency ranges. This is how you make different sounds. The letter E emphasizes certain frequencies. The letter O emphasizes others. The buzz is the same. The filtering changes. Your brain recognizes these patterns. You hear a voice, and you know who's speaking. The pattern is unique to that person. Voice recognition software does the same thing. It analyzes the frequency pattern, compares it to known patterns, and identifies the speaker. The pattern is the person's acoustic fingerprint. Music is patterns of sound waves organized in time. Rhythm is a pattern of when sounds occur. Melody is a pattern of which pitches occur in sequence. Harmony is a pattern of which pitches occur simultaneously. Your brain processes all these patterns at once, and you experience them as music. Different cultures use different patterns. Western music often uses specific scales and rhythms. Indian classical music uses different scales and elaborate rhythmic cycles. Gamelan music from Indonesia uses scales that Western instruments can't easily reproduce, but all of it is patterns of pressure waves. The patterns carry meaning, emotion, structure. The meaning is learned. The emotion seems more universal. Certain rhythm patterns make you want to move. The beat of dance music hits in a pattern that resonates with your body's own rhythms. Heart rate, breathing, walking pace. When external rhythm matches internal rhythm, synchronization feels natural. Your body wants to match the beat. Your heartbeat is a rhythm, a pattern of pressure, waves moving through your arteries. The pattern changes with activity and emotion. Doctors listen to this pattern. Irregularities indicate problems. A healthy heart produces a regular pattern with slight variation. Too regular or too irregular both suggest issues. Brainwaves are patterns of electrical activity. We've talked about the frequency bands, but the pattern matters too. Which regions activate in which sequence? The timing of activity across different brain areas. Consciousness emerges from these patterns. Thought, memory, perception. All are patterns of neuronal firing. Waves of activity coordinating across your brain. Your breath creates a pattern. Inhalation, pause, exhalation, pause. The rhythm soothes. It's one of the most reliable rhythms of your body. Meditation often focuses on breath because its pattern is accessible to conscious awareness. You can observe it, you can alter it, but it continues automatically if you stop paying attention. Ocean waves arrive in patterns. Groups of larger waves separated by groups of smaller waves. Surfers watch these patterns. They wait for the set. The pattern is somewhat predictable. Strong correlation between one large wave and the next large wave being nearby in time. The pattern emerges from how waves of different wavelengths travel at different speeds and interfere. Light from stars arrives in patterns. Spectral lines at specific frequencies. Each element produces a unique pattern when it emits or absorbs light. By analyzing the pattern of light from a star, astronomers determine what elements it contains. The star's light is a message written in frequency patterns. The pattern tells you the star's composition, temperature, motion. Radio signals are patterns imposed on electromagnetic waves. The carrier wave has one frequency. The information modulates that frequency or its amplitude. The modulation is a pattern. Your radio detects this pattern and converts it back to sound. The sound is another pattern. Patterns within patterns. Information encoded in the structure of waves. Patterns are how waves carry information. Pure sine waves carry no information. They're predictable. The interesting part is deviations from purity. Changes in amplitude, frequency, or phase. The patterns of these changes encode everything from speech to images to data. Without patterns, waves would be useless for communication. With patterns, they become the primary means by which information travels through the universe. Waves connect everything. The light you see traveled from sources near and far. The sound you hear connects you to events around you. The electromagnetic waves passing through you right now carry information from across the world. You exist in an ocean of waves, constantly bathed in overlapping patterns of energy. Your body produces waves. Heat radiates from you as infrared light. Your heartbeat creates pressure waves in your blood. Your muscles generate electrical waves. Your voice creates sound waves. You're not separate from the wave-filled universe. You're part of it. You contribute to it. You participate in the endless exchange of energy through waves. The universe began with a wave. The Big Bang sent a pressure wave through space. That wave became the cosmic microwave background. We still detect it. The universe rings with the echo of its own creation. The wave has cooled. The frequency has dropped. But it's still there. Space itself is vibrating with the memory of how it began. Waves will outlast matter. Long after the last stars burn out, after the last black holes evaporate, electromagnetic waves will still propagate through space. They don't need matter. They don't decay. The photons traveling through empty space will continue forever unless something stops them. The universe's last signals will be carried by waves traveling through endless darkness. In a way, you are waves. The particles that make you up have wave nature. The forces holding you together are carried by waves. The signals in your brain are waves. The sensations you feel arrive as waves. Your very existence depends on wave properties of matter. Without quantum wave behavior, atoms would collapse. Chemistry would be impossible. Life would never begin. When you watch ocean waves, you're watching energy borrowed from the sun, transferred through wind, moving through water. The energy will eventually dissipate, but it will never be destroyed. It will transform. Heat, sound, motion of sand and water. The wave will disappear, but the energy continues in other forms. Energy is conserved. Waves are just how it moves from place to place. If tonight's journey through the science of waves brought you peace, take a moment to like this video and subscribe to Simple Science for Sleep. Tomorrow night, we'll explore another wonder together. There are endless patterns in nature waiting to help you rest. Join us again, and tell me in the comments what topic you'd like to drift into next. This calming nature of waves might come from their fundamental simplicity. They follow rules, predictable mathematics. No matter how complex the pattern, it's built from simple components. Sine waves adding together. Interference creating complexity from simplicity. The rules are the same for ripples in a pond and gravitational waves crossing the cosmos. Perhaps there's comfort in knowing these patterns continue whether you observe them or not. Waves are moving right now through the ocean, through the air, through space. They moved before you existed. They'll move after you're gone. The patterns persist. The universe computes its wave equations constantly, everywhere, without thought or effort. It simply does what the mathematics requires. Your experience of waves is temporary, but the waves themselves connect you to something vast and eternal. When you watch sunset, you're seeing electromagnetic waves that traveled 93 million miles. When you hear thunder, you're detecting pressure waves from a lightning strike miles away. When you feel warmth, you're absorbing infrared waves. You're in constant communication with the universe through waves. The universe speaks in oscillations. You detect them. For a brief moment, you're part of the conversation. Rest now. Let the waves continue without you. They don't need observation. They'll be here when you wake. Reliable, mathematical, eternal. The gentle rhythm of energy moving through space. Tonight, let that rhythm carry you to sleep.